Hi everyone, my name is Aishwarrya and my matrix number is 225032, and today I'll be presenting about the first and second law of thermodynamics for the course EMM3226 Thermodynamics 1. So first, let me give you an overview of the concept of thermodynamics. Thermodynamics is the branch of physics that deals with heat, energy, and work. And the fundamental laws of thermodynamics is the first law of it and the second law of it. So basically, the first law will talk about the conservation of energy, and the second law will be relating concepts about entropy. For the first law of thermodynamics, it is defined as the change of internal energy equals to the change of heat and work. So we can express this mathematically equals to delta U equals to Q minus W. And it also states that energy cannot be destroyed or created, but it can be transformed from one form to another form. There are four types of processes where the thermodynamic properties of a system are generally ideal gas according to the first law of thermodynamics. For each of these cases, certain property will be constant, such as the temperature, volume, pressure, or heat. So the four processes are adiabatic, isothermal, isochoric, or isobaric. Let me explain the thermodynamic processes more detailedly. The first one is adiabatic, where no heat is allowed to flow in or out of the system, but the gas can be compressed or expanded. For the equation, we will use the first law of thermodynamics equation, but the Q will be substituted equals to 0. So now we will have delta U equals to negative work only. So for isothermal, the temperature of the system is constant. So when the temperature equals to constant, the internal energy will be 0. When we substitute internal energy equals to 0, we will get that Q equals to W. Next is isochoric, where the change in volume of the thermodynamic system will be 0, and when the volume change is 0, the work done will be 0. So according to the first law of thermodynamics, when W equals to 0, our equation will change into Q equals to delta U. And for an isobaric system, the pressure will be constant. So if the volume increases, the work done is positive, or else it will be negative. So it depends on the situation. And if we substitute W equals to pressure delta volume, we will get that delta U equals to Q minus P delta V. Now let me explain more detailedly what the second law of thermodynamics really states. So it states that the heat energy cannot flow from a body of lower temperature to a body of higher temperature without the addition of energy because of entropy. So entropy is basically the measure of randomness of a system, and it also will constantly rise in the universe as a result of any naturally occurring process. So mathematically, we can represent this by delta S universe is more than 0, where it means that the change in the entropy of the universe is more than 0. Under the second law of thermodynamics, there are few statements. So the first statement that we will look at is the Kelvin-Planck statement. So Kelvin-Planck statement states that it's impossible to design a heat engine that will convert all heat from a reservoir into useful work without losing heat to a cold reservoir. Basically, what a heat engine is that it converts heat into work, but it cannot convert all the heat into work because the sum of the input energy will be lost to the environment, and this will cause the thermal efficiency of a heat engine to be not 100%. It will be always less than 100% for a non-ideal system. Second, we will look at the Clausius statement. So it states that heat can't move from a cooler to a warmer body, basically a lower temperature system to a higher temperature system, without some change occurring simultaneously. So heat can only move in the direction of decreasing temperature. As we see in the diagram below, that scenario is impossible, so it would not occur like that. Lastly, I will explain about the Carnot statement, where it ensures the maximum efficiency of heat engines. Engine that operate in the cycle is known as the Carnot engine. For example, the cycle of an ideal gas Carnot refrigerator. Based on the pressure against volume graph, we can see that when the ideal gas expands isothermally, the refrigerator draws heat QC from a cold temperature reservoir. After the gas is compressed adiabatically until its temperature reaches TH, heat QH is discharged to a high temperature reservoir as the result of the gas's isothermal compression. So this gas will then eventually expand adiabatically to complete the cycle by lowering its temperature to Tc. And we can express the Carnot statement mathematically by using n equals to 1 minus Tc over Th, where n is the efficiency of the Carnot cycle, Tc is the absolute temperature of the cold reservoir, and Th is the absolute temperature of a hot reservoir. And both these parameters Tc and Th is expressed in the unit of Kelvin. Now let us explore the application of the first law and second law of thermodynamics. The complex engineering system that I choose to explain is the heat engine, specifically a diesel engine. So basically, a heat engine is a device that is able to convert the thermal energy into mechanical energy and vice versa. So how this works is that it absorbs a certain amount of heat from a high temperature source, and then this heat is converted to mechanical energy, and the remaining heat QC will be released to a cold reservoir. At the same time, some of the heat will be lost to the surrounding area, just like how we see in the diagram above. Let me explain more detailedly how the first law of thermodynamics has been applied for a heat engine complex engineering system. For a diesel transport, the chemical energy will be stored in the diesel engine and it will be combusted to produce heat. So this heat will subsequently be converted into mechanical work that it will cause the transport to move forward. So the concept of the first law that is applied here is actually energy cannot be created or destroyed, but it can be converted from one form to another. And for this example, basically it is chemical energy will be able to produce heat, and this heat will be converted into mechanical work. For a heat engine, the second law of thermodynamics also can be applied. So how can it be applied? Let me explain to you more detailedly. The efficiency of a heat engine in real life will always be less than 100%, and that of a diesel engine will be maximum efficiency of only 40%. The entropy will be always increasing due to the friction and unavoidable heat loss. So it's impossible to fully convert the heat energy into work. Therefore, the efficiency of a heat engine will always be less than 100%. Lastly, for this presentation, let me explain to you about the complex interaction within the system. So the interacting factors versus the conflicting factor. It is efficiency versus cost. So the interacting factor is, as the heat engine will be exposed to high temperature, pressure, and corrosive environment, high efficiency of the heat engine in such extreme operating conditions can be achieved by necessitating the use of specialized materials, for example, ceramic or superalloys. But the conflicting factor is that higher thermodynamic efficiency frequently requires higher cost material or sophisticated designs. So this might be limited by financial constraints. So the strategy that I suggest to resolve this is that governments, business, and academic institutions must work together to help the development of the efficient, reasonably priced technology so we can help to resolve this issue. Other than that, we can also reduce the development costs and take advantage of economies of scale by using standardized components. Thank you so much for watching my presentation. I hope that everyone have learned the first and second law of thermodynamics just like how I have.